Hey guys, Justin here. Before the video, I just wanted to let you know that all the footage in this video was taken from a marathon live stream we did on the main channel, where Michael did 7 final exams from 7 classes. If you're interested in watching the entire stream, it will be linked in the description. Hope you enjoy.
Let's find the equation of the plane containing the following 3 points. So let's say P is 1, 4, minus 1. Let's say Q is equal to 0, 1, negative 2. And let's say R is equal to 1, 0, 1. Okay, so if you recall, the classic information given to find the equation of a plane is a point on the plane, and you also need a vector which is normal to the plane. We're given 3 points, so hopefully we can derive a vector which is normal to the plane. So here's a bit of a picture of what's going on here. Let's say this is our plane, boom, like that. And let's say this is our point right here, P. This is our point right here, Q, and this is our point right here, R. So those are our points. But now out of those points, we can build 2 different vectors. And these 2 different vectors are not parallel. And that's because the points have been chosen like semi-carefully. So this first vector, which maybe we'll call V. So that's the vector from P to Q. And then we've got another vector here, which is the vector which we'll call W. That'll be the vector from P to R. So now we can take those 2 vectors and then calculate their cross product, and their cross product will be normal to the plane. So maybe we could draw that as this vector coming out of the plane like this. So I'll call this thing N, which is equal to, let's see, V cross R, but this was, or V cross W, but this will actually be W cross V, I think because of the right-hand rule. Okay, so that's kind of what we're going for here. And then once we have our normal vector, we can use that normal vector together with any of the points we want, and we can write down the equation of a plane and we're good to go. Okay, so now let's quickly calculate V and W. So notice that V will be equal to, well, I'm going to write this kind of in quotes. This works, but it's like the point Q minus the point P. So I'll write this as, in quotes, Q minus P. So we'll take Q, which is 0, 1, negative 2, and subtract P, which is 1, 4, negative 1. So 0 minus 1 is negative 1. 1 minus 4 is negative 3. Finally, negative 2 minus 1 is negative 1. So that will be my vector V. And then my vector W is equal to, well, I'll put that in quotes as well. So it's the final point R minus the initial point P. So I'll put this as R minus P. So same kind of thing. So I've got my R, so that's going to be 1 minus 1, which is 0. 0 minus 4, which is negative 4. 1 minus negative 1, which is 2. Great. Then I could scale this W if I wanted to, because all I need is a vector. It doesn't really matter its length, but we might as well leave it like this. Okay, so now N will be equal to W cross V, or V cross W. That just gives us the vector pointing down, but that's still normal to the plane. I'll take it to be V cross W because I'm like kind of annoying about alphabetical order. Okay, so we've got that, but then remember there's this matrix version of calculating the cross product. So we'll put our unit vectors I, J, K up here, and then we'll put our vectors V and W across the rows. So let's see, negative 1, negative 3, negative 1, then 0, negative 4, 2. Then let's see what we get. For our I component, which is the first component, it will be the determinant of this sub 2 by 2 matrix, which is in blue. And that's from crossing out this first row and this first column. So let's see, that'll give us negative 6 minus 4. So that'll be negative 10. That's our first entry. Good. Then our second entry will be the negative determinant of what we get for the submatrix, which I've built out of these orange. The negative determinant, because that's built into the determinant of the 3 by 3 with the J right here. So let's see, that'll be equal to the number 2. Okay, nice. And then finally, we'll have in our third component, our K component, the determinant of this leftover thing, which is 4. Okay, so we have something like that. But now notice that I can scale this because that doesn't hurt anything. It's still a normal vector. I'm gonna scale this to maybe 5, -1, -2, just by dividing everything by -2. I think that's a little bit nicer to work with. Okay, and then we're ready for the equation of our plane. So let's recall that the equation of the plane is the x component of this normal vector times x minus the x part of one of our points, then the y component times y minus the y part of one of our points, and the same thing as the z component. So it'll be 5 times x minus, we'll pick p maybe, 1, plus -1, so it'll be minus, and then y minus 4, and then minus 2, z minus -1, so that's z plus 1. So we have something like this. And then we could rewrite this as like 5x minus y minus 2z equals some number by like putting all of those things together if we wanted to, but I'll leave that to you to do that last bit of arithmetic. So let's say this one. So let's consider the following function. I'll call it f of xy, and it is the square root of sine of x times sine of y. So let's say it's something like this. So now let's first sketch its domain. So the domain here will be a subset of the plane because we've got a 2-variable function. We've got a 2-variable function. We're assuming that the domain is at most the plane, or some sort of subset that makes everything work out nicely. So let's notice that since we're putting this inside of a square root, what we need is for the inside of that square root to be bigger than or equal to 0. So we need sine of x times sine of y to be bigger than or equal to 0. Otherwise, we'll be taking the square root of a negative number. Okay, so that boils down to 2 possibilities. So possibility number 1 is that sine of x is bigger than or equal to 0, and sine of y is also bigger than or equal to 0. And then possibility number 2 is that sine of x is less than or equal to 0, and sine of y is also less than or equal to 0. Then you're multiplying 2 negative numbers and you get a positive number. So let's see, when is sine bigger than or equal to 0? Well, that's going to be between 0 and pi, and then all like 2 pi multiples of that. So maybe we could write this as x and y are in the interval from 0 to pi, and then like I said, all 2 pi multiples of that. But when we get to drawing the picture, we'll fill that in. And then what is this? So when are they both negative? Well, that's going to be when they are between pi and 2 pi. So this would be x and y are between pi and 2 pi. Okay. This was like not or, but and. So x and y are between 0 and pi. X and y are between pi and 2 pi. You can't have one and one the other. Okay, so now let's get our picture going. So we'll put a pi here. We'll put a 2 pi here. We'll put a pi here, and we'll put a 2 pi here. And then let's maybe checkerboard this. Well, I mean, that's maybe a giveaway using that terminology, but let's get this going right here. Okay, so both x and y being between 0 and pi is equivalent to being in this bit right here. Okay, good. Then both x and y being between pi and 2 pi would be equivalent to being in this bit right here. Notice that this portion right here is not allowed because one of them is positive and one of them is negative. Furthermore, this bit right here is also not allowed for the same reason. So now we can extend this essentially just by maybe copy pasting this and shifting by 2 pi. So I'll just do a portion of it, but I think we can see what the picture begins to look like. So you get something like that moving everywhere. Okay, so good, that's our domain. Now let's do the next thing, which is find f sub x times f sub y. So let's calculate that. In other words, the partial with respect to x times the partial with respect to y. So let's find f sub x first. So notice that f sub x views sine of y as a constant, whereas sine of x is a variable. But it's wrapped up in this square root, so we have to take that into account. So that's going to give us the square root of sine of y over 2 times the square root of sine of x times cosine of x. I believe we get something like that. And so that's of course using the chain rule, but we're in calculus 3 right now. We're not in calculus 1. So doing these like steps all at once, it feels okay to me. Okay, then let's see, fy, in other words, the partial with respect to y, will be exactly the same as that, except we're replacing x's and y's. And that's because this function is symmetric under the change of x and y. So we'll get root sine x over 2 root sine y, and then times cos y. And then the product of those, well, you just like put them next to each other. So there's not much to be said for that. So now let's do an optimization problem. So let's find local max min saddle points. Let's say this is our function. G of xy equals 2x cubed, and then plus xy squared, and then plus 5x squared plus y squared. So plus 5x squared plus y squared. Okay, so the first thing that we need to find are the critical points. So the critical points, and then we'll use the second derivative test for 2 variable functions to test those critical points. Okay, so let's find the critical points. So that means we need the partial of g with respect to x to be equal to 0 and the partial of g with respect to y to be equal to 0. I'm on purpose using different notation here just to remind us of all of the notation. So the partial of g with respect to x will be equal to 6x squared plus y squared plus 10x. So we need that to be equal to 0. So that's by taking the partial, keeping in mind that y is a constant with respect to x. Now let's take the partial with respect to y. That'll give us 2xy plus 2y plus 2y equals 0. And now you always end up with this like nonlinear system of equations. Well, not always, but often you end up with this nonlinear system of equations. And these like can be somewhat tricky to solve, but usually because most exam, homework, textbook type questions are constructed to work out nicely. They usually work out kind of nicely. So let's look at this one. I think this is the easiest one to work with. So let's see. This, we can factor a 2y out, and then we're left with x plus 1 equals 0. So that gives us 2 possibilities. Y is equal to 0 or x equals -1. And those are or, those are not and. So that means we need to look at each of them individually. Let's look at x equals -1 first. So putting that up here, we'll have 6 minus 10, so that'll be -4, y squared minus 4 equals 0. So that means we get y squared equals 4, which tells us that y is equal to plus minus 2, and we immediately have 2 critical points, -1, 2, -1, -2, bang. Now let's go to this next one. So our next case is y equals 0. So plugging that up here gives us 6x squared plus 10x equals 0. We can factor a 2x out maybe. That leaves us with 3x plus 5 equals 0. That means we get x equals 0 or x equals -5 over 3. So that's kind of gnarly because it's -5 over 3, but that's okay. So that gives us 2 more. Y equals 0, x equals 0, and x equals -5/3 and y equals 0. Okay, so let's test with the second derivative test. So the second derivative test uses this thing which I call the big D, which is equal to the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. And then we need to check if that's positive or negative or whatever. And then we also kind of compare that with just the second partial with respect to x. So let's look at the second partial with respect to x first. So gxx, so what will that be? Well, this was gx, right? So taking the derivative of this with respect to x will give us 12x plus 10. So we have 12x plus 10. And then notice at all of our critical points, except for this one, the second partial is positive. So note gxx at -1, 2, gxx at -1, -2, gxx at 0, 0, those are all positive. That means that we can start thinking about the second derivative test. If this thing is negative or 0, we can't really work with the second derivative test in this form. So in this case, gxx -5/3 0, that is less than 0. So that means that the test is not applicable. So if I remember correctly. So that means we'll focus on these 3 remaining critical points. So now let's calculate the big D. So the big D will be equal to 12x plus 10 times the second partial with respect to y. That means we need to take the partial of this with respect to y. That's easy, that's 2x plus 2 times 2x plus 2 minus the mixed partial squared. So I think it'll be easier to take the derivative of this with respect to x. Taking the derivative of this with respect to x gives us 2y. So we've got 2y squared, so that's going to be 4y squared. Okay, so that's our big D. And now we will evaluate this at all of these different places. And so 0, 0 will check. So if we plug in 0, 0, we'll get 20 minus 0, which is 20. Which is less than 0, sorry, which is bigger than 0. That means 0, 0 is a local minimum, right? Because the second derivative test gives you something that's positive, because both are positive. And then let's notice that the big D evaluated it, for instance, -1, 2. What does that leave us with? That leaves us with a negative number here, so -2 times 0 here, 0 here, then minus 4 times that, so minus 16, so this is less than 0. So this is a saddle point. Okay, so let's move on. So let's say we've got the integral from 0 to 1, then the integral from 2x to x plus 1 of f of y dy dx, and let's say we want to change the order of integration. That will mean we need to go from the integral from 0 to 1 of something dy plus the integral from 1 to 2 of something dy. So we need to figure out what those somethings are. Okay, so let's take the region expressed by these bounds of integration and draw it, and use that drawing to motivate how we'll change the order of the bounds of integration. Okay, so let's notice that we're going between x equals 0 and 1, so maybe we'll put x equals 1 on the plane. And then we're going y from 2x to x plus 1. So let's see, y equals 2x is something like, well, my scale is not great. Let's say this is y equals 2x. So that means my y scale is like compressed some sort of unit. And then here, this would be y equals x plus 1. So let's maybe draw that in orange. So let's say it looks something like that. Okay, so let's say this is 1 here on the y-axis. So, like I said, this yellow one is y equals 2x, and then this orange one is y equals x plus 1. Let's notice they intersect at x equals 1, which is y equals 2. So they intersect right here at 1, 2. Okay, so this is like motivating. I mean, a lot of it is kind of given to us. We see that we have to split this up, y between 0 and 1 and y between 1 and 2. That's because y between 0 and 1 is this portion right here, where the left curve is the y-axis and the right curve is y equals 2x. Whereas up here, the left curve is y equals x plus 1, and the right curve is y equals 2x. So that's why we have to split it up like this. Okay, so now let's get at it. So let's maybe put that off to the side, and then let's take our integral right here and rewrite it using this picture that we've just made. So this is going to be the integral from 0 to 1, and then the integral from 0 to y over 2, because we have to solve that for x, of f of y dx dy, because we changed the order of the integration, right? So we've got to replace this as, instead of a function y equals 2x, it's going to be line x equals y over 2. Okay, so there's that. And then we'll have plus the integral from 1 to 2. And then the leftmost curve here, solved for x, is y minus 1. So this will be y minus 1 up to y over 2 of f of y dx dy. Something like that. But now notice that this f of y is simply a function of y. So with respect to the inner integral, we can just bring it out. Same thing here. So that leaves us just the integral with respect to x in each of those places, which is very easy. We just have the upper bound minus the lower bound when all is said and done. So this will give us the integral from 0 to 1 of y over 2 times f of y dy for this one. Again, upper bound minus lower bound after taking the inner integral, keeping in mind that f of y is a constant with respect to x, and then integral from 1 to 2 of y over 2 minus y minus 1. That turns into 1 minus y over 2 when all is said and done, f of y dy. Again, because that inner integral is fairly simple in that case. So we get something like that. So that would be the blanks filled in. Okay, good. Now let's verify Green's theorem for a certain example. So verify Green's theorem for this particular example. Let's say we have the integral over the curve C, so it's a closed integral over C of y squared dx minus 2x dy. So that's the differential one form that we're integrating, although you wouldn't say that in Calculus 3. And then let's say this is our curve. So let's say this point here is the point 1, 0. This point up here is the point 1, 1. And then we connect that with the origin. We connect those two. Then we connect that with the origin. So this also contains the origin. And then we want to orient this in a certain way. Let's orient it positively, so counterclockwise. So let's say that's that. Okay, so let's calculate the line integral first. After we calculate the line integral, we use Green's theorem to calculate the associated double integral. Let's call this portion of the curve C1, this portion of the curve is C2, and this portion of the curve is C3. So let's go over the C1 portion first. So notice the C1 portion is simply along the x-axis, so we can parameterize that very simply. Let's notice that y is equal to 0 along the x-axis. That tells us that dy is equal to 0. And then x, runs over the interval 0 to 1, and dx is just dx. So we're parameterizing it with the variable itself. We're not like using a parameter t or anything. I think that's okay. So now let's notice our integral over that region looks something like this. It'll be the integral from 0 to 1. And then y is 0, so this cancels out. dy is 0, so this cancels out. So we have 0 dx, so that's just 0. So the integral over c1 of this form is in fact equal to 0. So that's not contributing anything. Now let's look over C2. So on C2, x is fixed at 1, but since x is fixed at 1, that means it's not changing, so dx is 0, and then we can parameterize the y part. So y is ranging between 0 and 1, going up this curve, and then dy is just simply dy, so we're parameterizing with respect to the only variable that we have. Okay, so now let's see what we have. The dx part's 0, so this is gone, and then we have the integral from 0 to 1 of -2 times x, but x is 1, so that's going to be -2, and then dy. So something like that. So, but that's pretty easy to calculate. That just gives us the number -2. So the integral along that second curve is -2. Okay, so now let's move on to the integral over C3. Now let's parameterize this. Notice that we're going back this way, so we'll have to be careful with our orientation. So this is the curve y equals x. That's pretty clear because it's a line from 0, 0 to 1, 1. And then let's notice that x is trending from 1 to 0. So let's write that down. It's trending from 1 to 0. And I'm going to write this in like kind of sketchy notation where it's on the interval from 1 to 0. That just means it's going backwards. Now, if I were writing this down more carefully, I wouldn't really write it like that, but I think we're okay here. Now, let's notice that since y is equal to x, dy is equal to dx. And that means on this portion of our curve, we have the integral from 1 to 0 of, let's see, x squared minus 2x dx. X squared minus 2x dx. But now we can just view this as a standard integral, and this would be the integral from 0 to 1 of 2x minus x squared dx by changing the order of integration. But then that gives us x squared minus a third x cubed evaluated from 0 to 1. But that gives us the number 2/3 because it's 1 minus a third. I think that's pretty clear. Okay, so putting this all together, we see that our line integrals, so our line integrals give us -2 plus 2/3, which is -4/3. That's what we get from our line integrals, just adding them up. I guess like plus 0, but I didn't write that in. Okay, so now let's apply Green's theorem. So Green's theorem said that this should be equal to the integral over the region D, where the region D is this, so it's the inside of the derivative of this with respect to x minus the derivative of this with respect to y. So that'll end up with -2 minus 2y. And then our differential area component. So again, that's our Green's theorem statement and result or whatever, that you can apply this and turn a line integral into a double integral. Okay, nice. Now let's see what our region is. So this is going to be the integral from 0 to 1, the integral from 0 to x of -2 minus 2y dy dx. That's because we're going y values between the x-axis and the line y equals x, and then we're going x values between 0 and 1. I don't know, if we were like real psyched, we could do this in the other order of integration, but I don't think it really is worthwhile here. Okay, so now this will be the integral from 0 to 1 of -2y minus y squared evaluated from 0 to x dx. which gives us the integral from 0 to 1 of negative 2x minus x squared dx. Okay? But then in the end, this gives us negative 1 minus 1/3. I skipped the kind of very last step there, but negative 1 minus 1/3 is negative 4/3, which matches what we get right here. So we got the same answer doing Green's theorem versus doing the line integral, and that's what you want.
Hey guys, thanks for watching the video. The link to the entire stream should be on the screen now, as well as the link to the next exam. We will be posting one every day this week, so make sure to check them out. And that's a good place to stop.